Okay, so let's continue. So what we learned before the break here is that if we use a symbol rate, RS, which is a little bit less than twice the bandwidth, then we can select pulses which are Nyquist pulses. Okay, and one such Nyquist pulse which is used in practice is a so-called raised cosine pulse, which has this hideous expression, but it's actually quite simple. So it's to show that this is actually a Nyquist pulse. Let's draw this. Okay, so you don't have the equation in front of you now, but you have to trust me on this one. So the Nyquist pulse or the raised cosine pulse in the frequency domain is a raised cosine. Okay. So what we have here is a plot of the Fourier transform of H. And it's equal to a constant t over 2 until the frequency 1 minus alpha over 2t. And then it's 0 after the frequency 1 plus alpha over 2t. And in between these two points, this point and this point, is a half period of a cosine, which is lifted up the horizontal axis. So if you think of a cosine, let's see if I can draw something which is briefly, if you can, with some imagination, you can think of this as a cosine. It can continue like this, for instance, right? Okay, so this is the raised cosine part. So it's something which is constant until this frequency and then goes down to 0 at this frequency. And then it's symmetric on the other side as well. So this is minus 1 plus alpha over 2t. And again, the symbol rate is 1 over t. Okay, so here we now have an expression of a pulse that we claim to be a Nyquist pulse. And how we're going to check this? Well, basically we take copies of the spectrum and we repeat that along the frequency axis and see when we add them together that we get a constant. So the next, if this is the next pulse in the sum in the Nyquist criterion is this one. It's the raised cosine frequency pulse centered around 1 over 2t, and that will look something like this. So it's a cosine like that, and then it becomes a constant like this. And we see that in the overlap between these pulses, we have two cosines, and if we add them, we get a constant. Okay, so to repeat, the frequency, the spectrum of the raised cosine pulse is something which is a constant until a part where there is a cosine that takes it down to 0, and then it's 0 for all time, for all frequencies, sorry. And the maximum frequency is this one. So what is the bandwidth of this pulse? Anyone? It's the maximum frequency component minus the smallest positive frequency component. The smallest frequency component is here. The maximum frequency component is here. So this is W. So it's 1 plus alpha over 2t. Okay. If we have such a pulse, this frequency pulse here, and then we take the next frequency pulse in the Nyquist criterion, that is, we take the black curve and we shift it to the right to be centered around the frequency 1 over t, we see that these cosines are completely overlapping with each other, and when we add them together we get a constant. Okay, and then we're back then we have shown that we fulfill the Nyquist criterion. So this will indeed give us intersymbol interference-free transmission. Questions? Okay. So, going back here to the equations, we see here that this is the raised cosine, the constant part, and then the cosine part. You can check yourself that everything works here. However, if we would like to have this in the time domain, we do the inverse Fourier transform of this, which is a nice exercise, and if you do that, you get this result. So, the raised cosine pulse in the time domain is a sinc function multiplied with something which is a little bit hard to see exactly what it is right now, but it's something that brings down the tails of the sinc function. So if you remember, the sinc function looks something like this. It starts like this and it goes down like that. So this is the sinc t divided by t. Okay, and it has 0 crossings every t seconds. Etc. So it's indeed a Nyquist pulse. The second, so the zeros, the right zeros we get from the first factor, and this one essentially just makes sure that the tails of this pulse dies off quicker. And it dies off according to alpha. So if we look at this in the time domain, we get something like this. So this is the raised cosine pulse in the time domain. And it better be that that we have 0 crossings every t seconds, like this. And we had that. And now this is plotted for different alphas. Okay. Here we can select alpha to be any number between 0 and 1. So it's a design parameter. So when alpha is equal to 0, then the raised cosine pulse is just a sinc pulse. And then we get, let's see, it's hard to see here, but it's the blue curve here. And we see that it's the biggest side lobes here. While if alpha is equal to 1, then we have this, we should call it some type of green curve here. And we see that it dies off to 0 quite quickly. Okay. So with the greater alpha, we have a larger bandwidth, but we have a shorter effective pulse, right? The more energy, the energy is more concentrated around 0. When we let alpha go to 0, we have a bandwidth that shrinks, which means that the time content of the pulse increases. Okay, it widens. Okay. It's like this. Bandwidth, time duration. It's like this. All right? If you increase one, you reduce the other. Okay. And this alpha here controls then the time behavior of the pulse and also tells us what the bandwidth is. So when alpha is increasing, we increase the bandwidth. Okay. Questions? Okay. So now we know that we have, and these pulses are used in practice. Okay, so they're practical, or approximations to this is used in practice. Okay, and what makes it non-practical is that this one extends from minus infinity to infinity, but we see that we can truncate this without much loss of the basic features of the signal. So in practice, one has to truncate this, but if we truncate it far away out, then it's very close to a Nyquist pulse, which means that the intersymbol interference is negligible. Okay, but we have now only specified what h should be. And remember that h is the convolution of g, the transmitted pulse, and the receipt filter. So how should we design those? Well, very often we would like to do it in the following way. So very often we want that f, the receiver filter, is matched to the transmitted pulse. We will talk about this criterion later on, but let's just imagine that this is what we want to do. So we want f to be equal to g and complex conjugated, so the star here, and then time reversed negative t here. Okay, so very often we would like this to be the case. Trust me on this for the moment. Okay, so what does that mean? Well, it means that the Fourier transform of f, so it's this curly f of small f, is g star of f. So if we have small f being equal to g star negative t, if we take the Fourier transform on the left-hand side and right-hand side here, on the left-hand side we get capital F. On the right-hand side, by just going through this integral, or you look it up in your mathematical table, you see it's going to be g star, okay, the complex conjugate of g. Okay. So what does this imply? Well, it implies that h, which is g, capital H, is capital G times capital F. Okay, so this we knew because why? Because we know that small h is the convolution of small g with small f. Okay, so if we take the Fourier transform, we get the product in the frequency domain. Okay. So this becomes then g of f, and f, capital F of f, is simply g star. So this becomes then the magnitude of gf squared. Okay. So to avoid ISI, we choose g to be a root raised cosine pulse. Okay, so what is the root raised cosine pulse? Well, it's a pulse whose Fourier transform is the square root of a raised cosine spectrum. Okay, so g of f is equal to the square root of the raised cosine spectrum. Okay, and this is okay because the raised cosine spectrum here is a real valued function, so nothing strange will happen here when we do this. So we just take the square root of this raised cosine pulse, and then we get another Fourier transform, and if we take the inverse Fourier transform of that, we get something called a root raised cosine pulse. Okay, so if we take the inverse Fourier transform of h, we get a raised cosine. If we take the inverse Fourier transform of g, we get a root raised cosine pulse. Okay. How do these look like? Well, here they are. So again, the Fourier transform of a RRC, root raised cosine pulse, it has the square root of the Fourier transform of a raised cosine pulse. If we do the inverse Fourier transform of the left-hand side and the right-hand side here, we get the time domain pulse being equal to this. Okay. So it's just what it is, right? It's very simple, maybe not so simple to derive, I don't know. It might take a while, but here's the end result. And this is what we care about. So for different alphas, this is what we have. Now, what's clear, however, is that if we take g and multiply it with itself, g squared, then g times g gets to be a raised cosine pulse. If we take the inverse Fourier transform of this, we get that the convolution of a raised cosine pulse with itself is a raised cosine pulse. Sorry, I'll take that once more because I said it wrong. The convolution of a root raised cosine pulse with itself becomes a raised cosine pulse. So these are very commonly used as the basic pulse in pulse amplitude modulation. And then if the filter is matched to this pulse, then we don't have any intersymbol interference in our transmission. And then everyone is happy. Questions? No? Okay. So let's move on then. So what we have done now is that we have looked at how to design pulses to avoid intersymbol interference. Okay. Now suppose we use these type of pulses. What should the rest of the receiver look like? Because remember now we're building up the receiver, and the thing we have figured out now is how to design the first filter, which is followed by the sampler. But what about the rest? Okay. And to figure that one out, we do a quick recap of some basic stuff that we talked about earlier, namely inner products, norms, and distances. So we remember that the energy of a signal is the signal magnitude squared integrated for all times. The inner product of two signals, x and y, is this integral. X times y conjugate integrated for all times. The length of a signal is denoted like this, is the square root of x inner product with itself, which turns out to be the square root of the energy of x. And the distance between two signals is the square root of the energy of the different signal. Okay, so we talked about this a few lectures ago. Minimum distance receiver, this is what we would like to achieve. So if we have a number of signal alternatives, capital M, and observe the receipt signal, what we want to do then is first to compute the distances. The distances between the receipt signal and the possible signal alternatives. So we compute this for L equals 1, 2, 3, 4, up to capital M. And then we get a bunch of distances. And then we choose the signal alternative as the one which has the smallest distance to the receipt signal. So if we plot the distances as a function of L, we find the smallest one, and then we take that L and say, okay, this is the index to the transmitted signal. So M hat here is the index to that signal alternative, which is closest to the receipt signal. Okay, so this is what we want to do. We observe the signal, we find the signal alternative which is the closest match to that. Once we have done that, we have a guess on which signal has been transmitted. Okay? Right. Notation alert. So, as you know, there are several books in this course. There is this main book, and then there are two electronic books that you find on the ping pong. You find links to these. And there is one book called Barry, Lee, and Messerschmitt, and we will use chapter 5 in that. And there they use notation slightly. So here, now the big change is that the transmitted pulse is no longer G, it's H. Okay. Which means that the criterion for Nyquist is that H convolved with F should be a Nyquist pulse. Previously it was G convolved with H should be a Nyquist pulse. Okay, so that's the difference. I'm sorry for that. I don't know why they changed notation in the book, but they did. So to be consistent with the book, we will also change notation. If I had written book, I would not have done that. Okay, the Nyquist criterion here, we will relax that slightly also to the following form, that H convolved with F, if we sample that every t seconds, it should surely be 0 when k is not equal to 0. However, when k is equal to 0, we don't insist that it's 1. It could be some constant instead. As long as this constant is non-zero, we're okay. Okay. Right. So the question is, how should we design F for best performance when we also have noise? Remember now that H times F, if we make sure that this is Nyquist, then we avoid intersymbol interference here. That's good. But the intersymbol interference is not the only problem we have. The other problem comes from noise, and noise goes this way through this filter. So we also want to design this filter to suppress noise as much as possible. Okay. And we haven't talked about that so far, so let's talk about it now. And it turns out that the best way to do this is to use a impulse response F which is matched to the transmitted pulse. Okay? Matched to the transmitted pulse means not, and I say not, that it's the same as the transmitted pulse, but rather that the impulse response is the conjugate of the transmitted pulse. Okay, it doesn't matter when you have real valued signals, of course, but then it's time reversed. Okay, so whatever pulse we have, h of t, then f of t should be a time reversed version of this. So if it looks like this for h, then f should look like this. Okay. So here we see that the transmitted pulse, which is this triangular wave, is not what f is. The matched filter is a flipped version of the transmitted signal, time reversed. Okay. Now, if we do that, if we have a matched filter, then we can use that in order to compute these inner products that we talked about on the earlier slide. Okay, so if we have some signal, whatever signal it is, R, and we feed it through a filter which is matched to H, okay, meaning that the impulse response is a time reversed conjugated version of H. Then we get some output Y, and if we sample that at time 0, we take just one sample of this, the output Y, which is the continuous signal Y evaluated at time 0, turns out to be the inner product between R and H. Okay, let's see why this is the case. Oops, wrong. So we have input R, and we have an impulse response which is H conjugate negative T, like this. Then we have an output, let's call it Y, which we sample at time 0 to get a number which we call Y, which happens to be Y, the continuous time signal evaluated at time 0. Okay? So this is the setup. All right, so what can we say about Y of t? Well, it's the convolution between the input and the impulse response. Okay, so now a small detour here. So I've seen this mistake made so many times that I think it's sad. I mean, I've done it myself multiple times, and I'm likely to do this in the future, but I'm getting less and less of these mistakes. So when we want to compute the convolution between two signals, r and f in this case, we know it's going to be an integral. So if we have an integral, we have to select a integration variable. It could be u or tau or v or x or whatever. It shall not be t. Okay? Anything but t works. T is reserved for the left-hand side here. Okay, so once you selected this, the only thing you need to do is to figure out what should be inside here. So we have a few choices here, and there's only one which is correct. Okay. So what should it be here? Any suggestions? Hint is should have something with t and something with u. U minus t, t minus u, u plus t, u squared plus t. What should it be?
T minus u.
There we go. Very good. T minus u and nothing else. Okay? Right. Back to this. Now, we would like to compute here y of 0, which means that we can put t equals to 0 in the right-hand side here, which means that we have an integral from 0 to infinity, and then we put in t equals 0 here, and then we get f minus u. Okay, so what do we know about f minus u? Well, f of t is what's inside this box here, namely h conjugate negative t, which means that f of u is h conjugate negative u, which means that f of negative u is h conjugate u. Right? So what we have left here with is the integral from minus infinity to infinity of r of u h conjugate u du, which by definition is the inner product of r of t and h of t. Okay, so this holds for any input r. So suppose the input is equal to h. So when r is equal to h, we have that y is the inner product of h with itself, which is equal to the energy of h. And this will be useful to have with us a little bit later. And E of h is the energy of h. Okay. Is it fine? Can I? Okay. Okay, so what we have shown here now is the following relationship, that the input r to a filter which is matched to h, sampled at time 0, gives us the inner product of the input r and h. Okay. A filter like this could be non-causal. So, for instance, when we had h, so look something like this, and we time reversed it, we certainly got something which was non-causal. Okay? Non-causal meaning that it's non-zero for negative t. Non-causal filters are unphysical in the sense that they look into the future, which is very hard to do. So they are unphysical, right? They're nice from a mathematical point of view, but they're not physical. So if we want to do something in practice, a real implementation of a matched filter, what we need to do then is to take the matched filter and then delay it a little bit until it becomes causal. So essentially move time 0 from here to here to make it causal. Then we have something which is a causal filter, right? So basically we take the matched filter and then we delay it by a suitable amount of time, t0, and then we can make f, the resulting filter, a causal filter, and then this will be the impulse response. And if we feed R with this causal filter, we get an output. And if we sample that at time not 0, but at that delay, t0, we get the same output y as we did up here. Okay, so we can just simply delay the impulse response, and then if we sample at a little bit later time, then we get exactly the same result. The difference between this filter and this filter is that this one is causal and therefore physically implementable. Okay. But anyways, we will not be afraid of non-causal filter for the mathematics of this course, but once you do your project, I'm sorry, you have to use a causal filter. You will see later on why this is the case. Okay. Now, let's go towards then the receiver structure here. So we're getting closer and closer to the best receiver we can do for pulse amplitude modulation. So far we have talked a lot about the receiver filter and how to design that, and then we get an output and then we sample it. And we know that yk is equal to ak if we have a Nyquist pulse when we convolve h with itself, when we convolve h with its the impulse response here. So we have no ISI if we take h, which is the pulse we use, and we convolve that with the impulse response of the receiver filter, which is this. Okay. So if we convolve them together and we get a Nyquist pulse, we won't have any intersymbol interference. Okay, so a Nyquist pulse, we get that by having all samples except the sample at time 0 to be 0, and the sample at 0 to be some constant. And we know that if h is input to a filter which is matched to h, we just show that the output of that is the energy of h. Okay, so, and the energy is something which is positive always, so a positive number here. So the blue parts here are true whenever h is non-zero. It holds for any h as long as h is non-zero. And the green part here holds true when h is a root Nyquist pulse. Okay, and go back to see a Nyquist pulse and a root Nyquist pulse. A root Nyquist pulse is when you take the pulse and you convolve it with the when you form this and you get a Nyquist pulse essentially. Okay, so for instance, h here could be a root raised cosine pulse, and this will work. Did I say it right? H here could be a root raised cosine pulse, and this will work. All right, so let's assume now that we have done this, so we won't have any intersymbol interference in y here. So y would be equal to ak if the noise is 0. Actually, it will not be yk. It will be, we will see that in a second what it will be. Okay. It will have no intersymbol interference at least. Let me say that. Okay, so yk, what we're going to do with yk now to implement the minimum distance receiver. The first thing we do is to divide by the energy of h. So this is multiplication with EH raised to the power -1, so this division with a EH essentially. And then we get Z, and then we feed that through this box here. And this box compares Z with all the elements in curly A. Remember, curly A are the possible amplitudes that we use when transmitting data. And then they pick the output A hat K which is the element of curly A which is closest to Z. So in mathematics, A hat K is the arg min of the difference between the input ZK and A, where we select A in curly A. Okay. So the output is the A in curly A, which is closest to Z. Okay. So the output is the element in curly A which is closest to the input. That's what it does. Okay. So you can think of it as sort of like a minimum distance box, right? It takes an input and then looks at the possible amplitudes and output the amplitude which is closest to the input amplitude. That's what it does. Okay. Good. Okay, empathy. So let's look at this receiver now. We know we're not going to have any inter-symbol interference. So instead of looking at the sequence of symbols, we just concentrate on the first symbol and see whether we can decode it. Okay. So this is called sometimes the one-shot receiver. With one shot, we mean we simply send one symbol, and we're trying to decode that. And this is no constraint, since we don't have inter-symbol interference. We know that the symbols are not going to interfere with each other. So if we can decode one symbol, say the 0th symbol, then we can compute every one by just repeating the process. So let us consider transmission of A0. Okay. Which is the symbol at time k equals 0. Okay, so it's the first in the sequence of symbols, A0, A1, and so forth. Let's just look at A0. Okay. Then we recall that we have mappings from bits to symbol index to amplitude to signals. Okay, so an example, for instance, suppose we need 2 bits, B0 and B1. That's what we will transmit using A0. So B1 and B0 could be 0, 0, 0, 1, 1, 0, 1, 1, for instance. Then this is mapped to some index M, which is 1, 2, 3, or 4. Okay, which is then mapped to the amplitude A0 as being either capital A1, capital A2, capital A3, or capital A4. Okay, these are the possible amplitudes. And then the transmitted signal S of t is A0 times H, which in the first case is just S1 of t, which is equal then to A1 times H. S2 of t is A2 times H. S3 of t is A3 times H. Can you guess what S4 is? Okay, it's A4 times H. Like this. So we have bits, symbol index, symbol amplitude, or transmitted signal. And they, you know, which one we use here doesn't really matter. It's just translation between the different things. Okay. So what we want to do then is to remember what we want to do. We want to be able to decode AK here. So it's better be that when it's noise free, that Z is equal to A. Okay, otherwise we're in trouble. Right? This is what we want to do. So let's see if that is the case. Y0 is the inner product of the received signal with H of t. Okay. So what we want to show is that when the noise is equal to 0, then Z of k is equal to A of k. Okay, so let's then look at Y0. So it's the inner product of R and H. And what is R? Where R is equal to the transmitted signal plus noise. But since we don't have any noise, it's just the transmitted signal. And what is the transmitted signal? Well, it's equal to A0 times H, inner product with H. Okay, what is this? Well, it's an integral from minus infinity to infinity, A0 H t multiplied with H conjugate t dt. Okay, we pull out A0, and then we have the integral from minus infinity to infinity, magnitude of H squared. And this is A0 times EH. Siri event told me. Okay. Okay, so this is Y. We now know that Y0 is equal to A0 times EH. And Z0 is Y0 divided by EH, which is equal to A0. So indeed, in the noise-free case, the input to the slicer is the transmitted symbol. Okay. Are we done with this? No, not really. So if we go back and look at our receiver structure here, what we have shown now is that Zk is equal to Ak when the noise is equal to 0. But we actually already sort of suspected that because we have chosen H to be a root raised cosine pulse, root Nyquist pulse, sorry. Okay. What we will show in the next lecture is that going through this step here, we produce the output here is the same as if we have used the minimum distance receiver, which is the best we can use. Okay, but we have to do postpone that derivation to the next lecture. So at the moment we are lagging a little bit in the lecture schedule, but I rather do that and not go too fast through these sessions. So if you believe that I'm going too slow, that's good if you let me know, and then I can speed up a little bit. Or if you think the pace is too fast, it's good that you let me know too, and then I can slow down. Otherwise, I'll just continue with this speed roughly. So, okay, but you can let me know. Okay.